Welcome to the Center of Math. For this week's problem of the week, we want to prove this identity. To prove this is rather straightforward. First, just consider the function. So we're going to look at the function sine x over x and consider some properties this function has. So consider f of 2x. So plugging f of 2x, we have sine of 2x over 2x. Sine of 2x is 2 times sine x over cosine x, all that over 2x. And this, because we know sine x over x is just f of x, so this equals f of x times cosine x. Now if we plug in for x over 2, we get, so we have f of 2x equals f of x cosine x. So plugging x over 2, we get, this becomes just x. This becomes f of x over 2. This becomes cosine of x over 2. Now here we can plug in x over 2 again and get something like, now we have f of x over 2 equals f of x over 4 times cosine x over 4. Now if we plug in this equation for f of x over 2 back in here, we get something. So now we have f of x equals f of x over 4 times cosine x over 2 times cosine x over 4. So we can keep repeating this procedure by repeatedly plugging in x over 2 here, and we get a general equation for f of x over 2 to the j of so we can say f of x over 2 to the j equals f of x over 2 to the j plus 1 times cosine x over 2 to the j plus 1. And doing the substitution like we did here repeatedly with these infinite equations, we can get something of the form. So yeah, by making use of all these equations, f of x over 2 to the j equals, etc., we can arrive at something like f of x equals f of x over 2 to the k times the product of from j equals 1 to k of cosine x over 2 to the j. Now this looks a lot like what we want. We just need to take the limit as k goes to infinity. And before we do that, we need to make sure everything converges. F of x over 2 to the k as k goes to infinity, that just is f of x as x goes to 0. F of x, remember, is sine x over x. As x goes to 0 for sine x over x, it's well known that this limit approaches 1. This infinite product, let's consider the sequence. Consider the sequence considering k equals 1, k equals 2, k equals 3, etc. Note that this product is bounded between 1 and negative 1 because each term in the product is bounded between 1 and negative 1. So this sequence is also bounded between 1 and negative 1. And one other thing, there exists a k greater than some m such that for all k greater than this m, x over 2 to the k is the absolute value of that is less than pi over 2. And this implies that cosine x over 2 to the k is somewhere between 0 and 1. Now, once this starts happening, this sequence becomes monotonic. Now, this is because once it reaches this point, if it's negative, we start multiplying by these positive factors between 0 and 1. It stays negative, but it starts only increasing because a negative number times a positive fraction gives you a negative number whose absolute value is slightly smaller. The absolute value will always be decreasing. And if it's positive, it stays positive. If it's negative, it stays negative. So it's monotonic. So this is a monotonic bounded sequence, and thus it must converge. So now we know as k goes to infinity, f of x over 2 to the k converges. We know this product converges. So we know the limit of the products equals the product of the limits. So we know this whole thing will converge. So taking as k goes to infinity, so the limit as k goes to infinity of this whole thing is the limit of the thing on the left times the thing on the right. F of x over 2 to the k goes to 1. This approaches some limit. We don't actually know what the limit is. We just know it equals f of x. And so doing all this, we arrive at what we wanted, that for x does not equal 0, otherwise this would be undefined. For x does not equal 0, sine x over x equals the infinite product of cosine x over 2 to the j. That's j from j equals 1 to infinity. And yeah, that gives us our solution, and then this problem is finished. Thanks for watching. Please, if you like this, check out our other videos on YouTube, check out our blog posts, and follow us on Facebook and Twitter. Thank you.